Alright, welcome back. So in this video we're just going to be doing some examples solving linear systems as matrices. But remember, linear systems are, in linear algebra, motivated by the question of finding the scalars that make a linear combination of a certain set of vectors, in this case 3, 1, 0, negative 1, 0, 2, and 1, negative 2, equal to a certain desired result vector, which in this case is negative 1, 2, 0. So what scalars x, y, and z make this linear combination on the left equal to this vector on the right? Well, if you recall, the first thing that we do is we write this as a system in matrix notation. The first row represents the first linear equation that we would get solving for the first component, where the second row represents the second linear equation, and the third row represents third linear equation. So this is just a linear system. And we're going to be using Gaussian elimination to solve this system. I talked about that in the last video. Now you'll get a clear picture of what that is through example. The first thing I like to do in Gaussian elimination is I look at all of the elements on the far left of the matrix. And if any of them are ones, then I do row swapping so that the row that starts with a 1 is the first row. So in this case, the first row starts with a 3 and the row below that starts with a 1. And so I'm just going to switch those, and that will just make the process a bit more organized. It really doesn't do anything mathematically significant. Row 1 swaps with row 2. And that will look like this. Negative 1, 1, negative 1, 0, 2, negative 2, 0. So now, with a row combination, I'm going to use the first element of the first row to make all of the first elements of the rows below it equal to 0. So in this case, the third row already begins with a 0, and that's good. And the reason why is because I need all of the entries along the main diagonal to be 1s in Gaussian elimination, and I need all the entries under the main diagonal, which are these 3, to become 0s. Okay, so the first thing I'm going to do is I'm going to do negative 3, row 1 plus row 2. In that case, we're going to have, well, the first row is unaffected because it's just the row that we're sort of sourcing our elements from, but it's not the one that's actually affected at the end of the operation. The third row changes because I'm taking negative 3 of row 1 of all the elements in row 1 and adding them to the corresponding elements in row 2. Negative 3 times 1 plus 3 is 0. Negative 3 times 0 plus negative 1 is just negative 1 because the 0 is unchanged. Negative 3 times negative 1 is 3. I add that to 1. We have 4 here. And then negative 3 times 2 is negative 6 plus negative 1. That's negative 7. And the third row is unaffected. It was not involved in the operation to begin with. These 2 are now 0s. And now we just need to affect this 2 here. We need to make that 2 a 0. And to do that, I'm going to do another row combination. We're going to use the second row to make the leading entry of the third row a 0. The leading entry is the first non-zero entry. How might I do that? Well, what if I took 2 of row 2 and I added that to row 3? 2 times negative 1 plus 2 is 0. So let's just write out this matrix now. So the first row remains the same. The second row remains the same because that one was not the one that's actually affected by the operation. The third row changes in the following way. So 2 times 0 added to 0 is just 0. 2 times negative 1 plus 2 is 0. 2 times 4 plus negative 2 is 6. And 2 times negative 7 plus 0 is negative 14. So the last part of Gaussian elimination is going to be making all of the entries on the main diagonal, which is this negative 1 and this 6, and this 1 over here also, equal to 1s. And I'll do that by using row scaling. So I'll take negative row 2, and I'll take 1/6 row 3. Row 2 changes into 0, 1, negative 4, 7, and row 3 changes to 0, 0, 1, negative 7 thirds. And this is row echelon form, and I'll abbreviate that REF. We could technically stop right here. Here's how we could convert this matrix back into a system of very easy to solve linear equations now. This last row here says that 0x plus 0y plus 1z is equal to negative 7 thirds. So in other words, that's the value of z right there. Z is equal to negative 7 thirds. What does the second row say? It says that 0x plus 1y minus 4z, but z is equal to negative 7 thirds, so it's really minus 4 times negative 7 thirds is equal to 7. And if we solve, we find that y is also equal to negative 7 thirds. And the first row says that x plus 0y minus 1 times z, so minus negative 7 thirds, is equal to 2. Say that 2 is the same thing as 6 thirds. So x plus 7/3 is equal to 6/3. So x is equal to negative 1/3. And these are the values of x, y, and z that we get. And this method of taking our matrix to row echelon form and then starting with the bottom row, which gives us explicitly the value of one of the variables, and then substituting back up into the upper rows, is called back substitution. So it's not just solving a linear system, it's solving a linear system that is much easier than the first one, because we don't have to do any complicated substitution, we don't have to do any elimination with equations. We did sort of elimination with our rows here, and so the substitution is much easier. However, this is really not the best way to do it. Once we convert our system to a matrix, we actually want to keep it that way. We're essentially going to do the same thing with the matrix that we did right here, using matrix operations. We're going to take this matrix to an even more simplified, more reduced form, reduced row echelon form. And this was the matrix in row echelon form. Now we're going to take it to reduced row echelon form, and I'll show you what that looks like. So this is the matrix in row echelon form. We have a main diagonal of only ones or zeros. In this case, they're all ones, but they could be zeros. And all the elements under the main diagonal, these three right here, are zeros. And what reduced row echelon form is essentially we take all of the elements that are above the main diagonal, which are this 0, this -1, and this -4, and we're going to make them all zeros. So one of them is already 0. We're just going to use row combination to make those into zeros. I think that we should do 4 times row 3 added to row 2, and similarly, we should do row 3 added to row 1. And notice, even though I'm sourcing both of these operations from row 3, I'm affecting row 2 and row 1 independently, so I can really just do these at the same time. What would that look like? How is row 2 affected? We have 0, 1, because the zeros beneath them multiplied by 4 and then added to these entries above in row 2, leave them unaffected. And we have 4 times 1, which is 4, added to -4, which leaves us with 0. And then we have 4 times -7/3 added to 7, which is also -7/3. Finally, we have row 3 added to row 1. 0 added to 1 is 1. 0 added to 0 is 0. 1 added to -1 is also 0. -7/3 added to 2 is -1/3. If you notice, these are exactly the values of x, y, and z that we found above. We're essentially doing the same thing that we did above when we were solving these equations right here. We're just doing it in matrix form. Each of these rows are equations for explicitly x, y, and z. The first equation, the first row says that 1x plus 0y plus 0z equals -1/3. That's explicitly the value of x. And similarly, we have that for y and z over here. And once we find the possible values of x, y, and z, we can describe those possible values using what's known as the solution set. We can actually describe the values of x, y, and z in a vector. So let's say that we have this vector, x, y, z. For our possible values of x, y, and z, again, these are the coefficients of the linear combination of the vectors which made up the columns of the original matrix, and that linear combination using these coefficients was supposed to equal that desired vector on the right. The possible values are simply -1/3 only for x, -7/3 only for y, and -7/3 only for z. So it's just this set of one and only one vector where the possible values for x are the first component, the possible values for y are the second component, and the possible values for z are the third component. This is the solution set to that matrix.